Hey everybody, this is Larry. This is me doing Q4 of the weekly contest 346 modified graph edge weights. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. So first of all, this one is kind of hard. This is a very hard problem. I guess I end up doing. I took a long time, but apparently it did well compared to whatever. So I don't know what to say. Maybe I don't know. It was very tiring. I think there are a couple of things, right? The first observation is that if the shortest path is already, um, if the shortest path is already faster than um, the target or the target, then it's not possible, right? Because no matter what you do, it's yeah like if no matter what you do, you cannot make it higher, right? That's just there's already a shortest path. You can't make change the shortest path, and the way that you would emulate that is, of course, it's just by changing all the edge weights to the max number, which is 2 times 10 to the 9, right? And then the opposite is also true. If you set all the weights to 1, if you cannot lower the shortest path, that means to at least under the target. That means that it's also impossible, right? I think the hardest thing to prove for me is that, and it took me a while. I was a little bit YOLO and thinking about this during the virtual contest. The hardest thing is figuring out that let me adjust my sitting a little bit. The hardest path is figuring out that you only need to change one edge weight. The reason is that I think the core thing is understanding that shortest path algorithms are all, well, I mean, maybe not all, but for non-negative weights are greedy, right? You can use Dijkstra, you could use whatever. There are a couple like Bellman. What's it Bellman for? But in any case, they're based off this idea of greedy, right? Where you always take the shortest thing on everything, right? So let's say in this shortest path, you use one of these unweighted edges, right? Well, then obviously the proof is very straightforward. The proof is very straightforward because, let's step back for a second, right? So let's say the shortest path without any edges modified, or you could inversely say, or not inversely, sorry. Another way of saying it in modeling is that if you change all the -1 weights, the modifiable weights, if you change them to infinity, if the shortest path is equal to target, then you're done, right? I mean, obviously, doesn't change, right? However, if it's higher and you change one of the edges and that changes your shortest path to target, well, then of course you only need to change one edge. However, if one edge is not good enough, you need two edges on the shortest path, right? Well, if there are two edges on the shortest path, that means that by definition, changing only one of them is not good enough, right? Because if you can change only one of them, then you would have already done so. Yeah. And basically off that, off that, you can prove that in that way, given one critical path, it doesn't matter how many edges you're modifying. Only one of them has to be non-1, right? Because if the shortest path goes for another way, then by definition, you can remove one of the remove your non-1 edge, and then it would have gone another way, right? And then you could have put that weight into another edge, right? So by that, you can kind of prove with induction that you only need to change one edge to get the answer if it's possible. The second part that you have to make an observation about and prove is that that in a greedy kind of way, it's okay to because basically for this problem, you have to modify all of them, right? In how they say it. Of course, technically you just set them to infinity or max or whatever, and that's I consider not modifying, but whatever. Because you're not trying to minimize the number of things that are not one or whatever. You can actually, decompose them, right? Meaning if the shortest path goes through two edges or two of these -1 edges, then or maybe going the other way, right? Let's say, sorry, I confused myself a little bit. Basically, if the shortest path can go through one edge, it's okay to have another edge that's not used. That part is obvious. If we modify it and we don't use it, that's fine. But if we do end up using it, it's the same. It's just that instead of, let's say in the simplest case, you have an edge list of 3 nodes, 2 edges. It doesn't matter whether, well, in this case, I guess it has to be. How do I say in a better way? But what I want to say is that if we change one of the edges to 1, and then there's a shortest path that goes with one of them, that's fine, because you're not trying to minimize the number of edges you minimize as long as you're able to find one. And having one of previous edge set to 1 doesn't change the feasibility, right? I guess that's maybe the way to say it, because basically without that one edge, it just means that your other edge will have to be x plus 1. You have to have the weight plus 1 to meet the target, or maybe not even possible, right? So that's basically the idea. And in that way, you could just do them arbitrary, one edge at a time, and binary search one edge at a time to see if it's possible, right? So let's go through the code. Hopefully that made sense a little bit. Maybe not. My apologies. I'm still traveling, so I would like to draw stuff, but I don't have the tools today. But yeah. But basically, I wrote. So this is okay, right? So basically, we create a graph of just the edges, not including the -1 edges, but and we'll have them later. We call them add edges. I don't know. It's not a creative name, but yeah, we create an edge and edge list, an adjacency list, and then we calculate, right? We calculate it for the base list. If basically the graph without the -1s, if that's already better, lower than target, that means that's not possible, right? Because whatever you do can only make, like, it's not going to change the shortest path, right? So that's why we do nothing. If it's equal to target, then we're already done. So then we just convert I have this helper function that converts an edge list that we have, or we convert the edge list to basically the answer of all the edge weights, right? If it's -1, then, or if it's not -1, meaning it's an original edge, you can't change it, we obviously just add it to the answer. Otherwise, we look up what we stored for it. If it's not in the lookup, we set it to the maximum number, which is 2 times 10 to the 9. And of course, given it the target, it's only 10 to the 9. That means that it's not going to be possible anyway, or you'll never use that edge, is what I mean. So that's basically get the answer, right? If it is bigger than target, then we do make an attempt to solve it. Basically, we have a progress of all the edge that we've used so far. um, we start by add an edge of weight 1. Is it possible? Right? And this is my Dijkstra algorithm. Let me go over it very quickly. I set an option so that you can add an extra edge with weights. If it's not none, then we set UVW as you go to option. We put it into the graph, and then at the end we pop it so that we kind of reset, right? And we return the distances. The rest is a Dijkstra's algorithm. I'm not going to go over it because the rest of this farm is hard enough. So if you don't really know Dijkstra, you're going to struggle. I had some typo here during the contest. You can watch that, but that's basically the idea. And yeah, and if adding this edge as 1 doesn't change the or at least doesn't make the answer possible, because that means it's still not possible, right? Because the best shortest path, it's still bigger than target, so that means it's not possible. So we just set it to 1, and then we add the progress here. Otherwise, maybe it's possible. So let's give it a look, right? So this is a binary search. The edge rate could be 1 to max, which is 2 times 10 to the 9. Technically, yeah, it should be okay. I think technically you only, I guess maybe that's fine. I don't know. I mean, it's not even, I think technically you can actually search this to be the target, whatever, right? It's just a little bit slower, though maybe I should have made the optimization. The rest is a regular binary search. So you do a calculation on adding this edge with mid as the rate. If the shortest path is still bigger than target, you have to make the rate smaller. If it's smaller than target, you have to make the rate bigger. Otherwise, now is equal to target, which means we're done. So let's set everything to mid. And then here now we calculate it again just in case. But basically, if this is equal to the target, then we can return it as the answer. Otherwise, that means that we're not able to get the answer. It could be under, it could be over. We just don't get the answer. So then now we continue and do it for the next edge. That's basically the idea. And we can go over the complexity real quick. So this is Dijkstra. It's going to be log e. So this is roughly speaking. V is equal. Let me write it here, right? V is equal to 100. Log e is equal to, what is it? So number of edges is like 10,000 or 5,000. So that's going to be what, 20 or something like this? Oops. No, that's not even 20 is a million. So like 16 or something. I don't know. You could do the math. 2 to the 15. No, 15 is already too big too, right? 2 to the man, I'm really struggling today. 2 to the 10 is 1,000, so just double it twice, right? What am I doing? Well, so yeah, so like 13, right? So this is pretty fast for Dijkstra. Is my point. You don't have to worry about it. And so this is relog e, right? Everything else is linear, or not everything else, but this is linear. This is linear. So this is relog e. But this is very expensive. This is going to be log of r, where r is the range. And of course, with 2 times 10 to the 9, it's just going to be 32, say, right? I guess 31 or whatever, but close enough, right? 31, 32. So that means 32 times all of relog e. What did we say it was? Relog e is like is 100 times 15 or something, or 13. So this is going to be fast enough in theory, right? Yeah, right. So this is relog. Yeah. So that means that this loop is total relog e log r, right? But we have one more loop, which is the number of edges. The number of edges is at most 5,000. So this is going to be the expensive one. Yeah. Well, this is just O of e, right? So in total, this is v times e times log e times log r, which is not great, to be honest, because v times e is going to be close to like 1,000,000, right? It's like half a mil times 10 times log r kind of adds up, but keeping in mind that a lot of these are not possible, so, and it kind of converges very quickly, so that's maybe how I justify it. If you ask me, maybe I should have done this C++. Let me actually double check the running time. I actually don't know how long that took, but yeah, it actually went pretty fast. But yeah, I suspect that there's a lot of cell pruning involved because you're not going to get the full thing every time, because you don't, because way before that, because there's some balance between. I'm justifying a little bit. I don't know if it makes sense, but add edges can be, if add edges is ye, that means that every edge in the worst case is going to be there, but that also means that you only need to get 100 of these to kind of get it right. Maybe a little bit more, like say 200 if you're having unlucky, if you have an adversary or something like this. You can fix someone like challenging you by just like randomizing the order of add edges so that it's like probabilistically unlikely. But in any case, like let's say you have 100 edges or 100 nodes, if or 100 choose 2 edges are negative ones, you only need like 99 of them, right? So I don't know, at some point you are going to connect the graph, and that never runs, that doesn't run v times z that much, maybe, I don't know. That's all I have though. Let me know what you think. Let me show you my code again real quick. Make it slightly smaller. So this is just set up the edge list. This is the Dijkstra algorithm. This is converting to the answer, the beginning of the calculation, and then this is the for loop that does the magic with the binary search in the middle. Maybe I should put the binary search in a separate thing, but I don't know. But yeah, that's all I have for this one. Let me know what you think. Let me know how you did. Yeah, you could watch me solve it live during the virtual contest now. 1478, 182. All right, let's go. That was annoying. How am I doing so far? 15 minutes and I'm not that fast. But 81st, not that bad. I was too slow in Q3. Oh well. Wait, what? Oh, I cheated a little bit. I wish they don't show you this on virtual contest. I peeked at total accepted and it's 93, which is obviously, but right now no one seems to have done it yet. N is equal to 100 Target is some big number. This is a hard problem, graph problem. Should I put more soda? I wish they showed the original, the given graph too, because this is confusing. Or not confusing, just like hard to kind of see what they did. 0 to 2, -1. Oh, the entire graph is -1. I wonder if you could just cheat. No, because let's say you have a linked list. Like my question is try to figure out whether you need to modify more than one edge. Let me look at the constraints. N is 100. Edge can be any number of edges as long as whatever. The shortest path is going to be at most n nodes or whatever, n minus 1 edges. Does that mean anything? If we set everything to 0, what does that mean? That means we can check whether it is possible. So let's say we set everything to 0, and then we set everything to some big number, infinity. Then if it's in between, then I guess it is. But I guess my question is, do you always, like, can you modify more, just one edge, right? Like there's a critical path. No, because then this is a problem I really need pen and paper for. Unfortunately, I'm stuck in a hotel room thinking, so I have to use my small brain to visualize everything. No, because you can have like a diamond thing. What would the diamond, multiple diamond things that forces you to probably do multiple edges, right? Maybe. Still no one got it, and it's been half an hour. That's actually not very, well, I mean, at least the Americans. I guess the Chinese maybe, but... Can you always... Like if it's between the shortest path where all the negative ones does it wait, does that have to be, oh no, it has to be positive. Oh no. Oh no, yeah, you have to modify to make positive. Well, I mean it's the same thing, so you set everything to 1, Is this? Don't tell me this is a max flow. Okay, you set everything to 1. So then, if it's under target, then whatever. And if it's infinity, then it's also too big. Oh, right. So then how do you do it? There are most 10,000 edges. That's tough. Like, one idea that I have is like a repeated Dijkstra, because with Dijkstra you could get the second shortest path, and with the second shortest path you can change one of the edges, but I don't even know if that works. I don't even have any idea right now. And you have to want to make it exactly to target. Is it always possible? No, because your second shortest path may be smaller than target, or just the shortest path that doesn't require a -1. Can I set this up as a max throw? How would I set it up as a max throw? Trying to think. Oh. No, that doesn't make sense. You can't really. No, because then you have paths. No, that doesn't make sense. Yeah, I mean, I don't know. I think the biggest thing is trying to think whether just one edge is good enough. Okay, let me think. So, okay, let's say the shortest path, the current shortest path without the negative ones, it has to be by definition bigger than the distances. So if we add an edge of 1, then either it brings it down, and if it brings it down, then we could maybe binary search to see this works, but I don't know. Does the order of operation matter? Well, I guess the thing is that I guess there is some proof where I don't know. I don't know if I could prove it right now, but let me play around with it. I think the thing that I try to do too much is proving during a contest, and I know that this is a virtual contest, but I should maybe still, I don't know, use my normal notations. This is too much to type. Is it undirected? Okay. That's what I thought, but I just want to make sure. Okay. Just write it live, shortest path. Yeah. I've been writing this one incorrectly. I had to make sure that I write this correctly. Yeah. 4 people got it. Ridiculous people, so I don't know. Alright, but you know what you're doing, Lavish. Just do it. Okay. What am I doing? I already did that. Oops. Okay, so then we do empty arrays. I guess I have to check this first. I mean, no, I guess we don't need to add it. We just no, we assume it is 1 now. I guess it's less than target. Then we binary search. And you stop typing that. Except for it's not 0. Otherwise, maybe it's possible, but we have to test the weight. So we want something like $50. It is too slow. 50,000. 100 times 100. No. So 5,000. 5,000 times n square. That seems a little bit slow. Maybe I should have done in C++. Whatever, it's too late. Maybe I'll just use ChatGPT to convert. If it's too big, then we want to try something smaller. If it's too small, we want to try something big. I think this is roughly right. I don't know if it's fast enough. What are you doing there? Whoop. Let's see. Not once, huh? From 0 to 1. Where's the last edge? Oh, 3. That makes sense. Okay, fine. No, it doesn't try it at all. Why is that really infinite? Am I thinking? Do I not know how to do dice draw? Why is that never right? We populate all the damn things. I cannot code today. Let's target again. 1. Literally, we have a 1 thing and it's 3. I mean, I could change this, but I don't know why. Oh, did I mess up target somewhere? I don't get it. Why is it going to be away from bounce? 5. Oh, target isn't the, you dummy, you mean destination. Oh my god, I've been confusing target and destination. Okay, fine. Okay, I mean, other stuff is whatever, but at least that's a real error and not a Larry debugging error. That's definitely not right, but I don't know what the last one is, so maybe just lucky. I mean, it's just lucky because maybe you set it to 1, it works. Which obviously, did I get the order wrong? Okay. If now is. If now is too big, how to make it. Yeah, I think this is a little bit awkward. Is it? Where's the target? That's right, right? Oh, I'm dumb. What I need to do, I think I. Oh, whoops. I thought I could get away with it. I used to be somewhere. What bug did I introduce? Oh, I see, because I don't pop it from here. It's giving me n, so I don't know if it's good to... I guess we can verify, really. So not the same, right? 4, 3 is 3, and the other ones are 1s. Guess that looks good. YOLO time. No, I forgot to check for running time. Well, maybe time's out. Oh. Yeah, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.